All right. So good morning and welcome to the next edition of our 2024 CEBRA webinar series, or as they have become well known as CEBRAnars. My name is Lisa Skorowski and I'm an Assistant Director in our Research and Innovation section within the Biosecurity Strategy and Reform Division. I recognise and acknowledge the Aboriginal people of mainland Australia and the Torres Strait Islanders as the first people of this country. And for myself up here in Brisbane, I acknowledge the Turrbal and Yuggera people as the traditional owners on whose land I meet on today and pay my respects to their elders past and present. Knowing that we're all tuning in from many different places today, feel free to pop in the chat where you're joining us from. Before we begin, can I ask that everyone has their microphones on mute and your cameras off? This webinar is being recorded for those who can't make it today, and there will be an opportunity to ask questions after the presentation. So you can either use the hand up gesture or post a comment question in the chat panel. For those joining us for the first time, the Centre of Excellence for Biosecurity Risk Analysis, or CEBRA, is a long-standing biosecurity research initiative currently hosted by the University of Melbourne and plays a vital role in providing the Australian and New Zealand governments with expert biosecurity risk analysis and advice that helps inform a range of biosecurity risk management activities. Today, we'll be joined by Dr. Tao P. Lee, also known as TK, and they will be presenting on estimating pest and disease consequences, a myrtle rust case study. TK is a research fellow at CEBRA for data science and the School of Mathematics and Statistics at University of Melbourne. They graduated with a PhD from University College London in quantum physics and is now working in mathematical biology and biosecurity. TK has extensive experience modelling COVID-19, including delivering modelling to support global vaccine policy, and has worked on several projects for DAFF to support biosecurity decision making. Today, we're also joined by Pip Griffin, Director of Biosecurity System Modelling here in DAFF. Pip has worked as a research scientist for several years and has been part of the Biosecurity System Modelling team since 2019, leading efforts on software uplift, transparency and communication. Pip was the DAFF lead for this project and will provide us with some initial insight to get us started. So without further ado, Pip, over to you.
Thanks, Lisa, and thanks everyone for coming today. So as Lisa mentioned, I'm from the Biosecurity System Modelling section in Biosecurity Strategy and Reform Division. My section was the departmental lead area for this project, which was developed to support our work on system-level biosecurity risk. So the historical remit of my section has been to provide insights to senior decision makers around biosecurity risk, impact, and expenditure at the system level, at the whole of biosecurity system level, which is quite distinct from some of the more some of the other analytical work being done throughout the department and elsewhere that is tackled on a more granular and detailed level. So to be able to estimate biosecurity risk across the system, as with other levels of risk estimates, we need to understand the probability of pest and disease entry, establishment and spread, as well as the impacts or consequences of that entry, establishment and spread. And this CEBRA project helped us fill in that second piece of information. It helped us expand and update the suite of consequence estimates that we can use in our system modelling. But because TK and team took the approach of developing impact estimates for individual example pests and diseases, they can be reused in many other contexts. And the benefits of reuse were considered in the project design, in the development phase, and in the choice of exemplar pests. So I would like to thank everyone from the environmental biosecurity area in particular and elsewhere in the department who were involved in all the early consultation and the expert elicitation efforts on this project. So I think I will hand it over to TK now, but just to, if anyone is interested in hearing more about our rationale for supporting this work, or wants a copy of the report, which is on the CEBRA website, or to chat about it, please get in touch. I'll put our team email in the chat. And over to you, TK.
Thanks, Pip. Yeah, that was a really good introduction. So this project, let me see if I can move the slides. Okay, so I also want to acknowledge traditional owners of the lands on which we work, learn, and live. So this work was done particularly on the lands of the Wurundjeri Woi-wurrung people and the Bunurong peoples. And I want to pay my respects to the elders past, present, and future, and extend that respect to other Indigenous Australians who are here today. So this CEBRA project was worked on by 23C was worked on by 4 people: Chris, Meryl, myself, and Tom, and we had kind of different roles. Chris did most of the leading of the project. Meryl did a lot of the modeling. I did some reporting and assistance, and Tom kind of overviewed the economic analysis. And on the DAFF side, as we mentioned, HIP is the director of the Biosecurity System Modeling section and of the Risk Intelligence and Strategy branch in the Biosecurity Strategy and Reform Division. And Mira was also working with us, is still working with us on data analysis. Before PIP came, we were actually also working with Vivian, Adam, and Ellen, who have all now left DAFF. So as Pip was talking about, the context of this work is about whole system modeling, and the BSM section has a suite of models for whole system strategic overview of the Commonwealth biosecurity system. So the 2 flagship models are the risk return resource allocation model, or CEBRA model, and that estimates overall and per pathway value of risks mitigated by the biosecurity system, as well as estimates expected rates of entry of pest and disease functional groups. The value model is the second flagship model, which is the one that we're going to talk about today. It's co-developed by CEBRA. It estimates the overall value of the Commonwealth biosecurity system based on damages avoided. And it also does use input from the CEBRA model, so particularly the entry rates of pests and diseases. So for those who don't know the value model, it was developed over several years previously, with the first kind of version finalized in 2020. And it was worked on by primarily these 4 people: Aaron, who led the project; Natalie, who did a lot of the economic analysis; John did a lot of the coding; and Tom, who also, I think, did economic analysis as well as like overseeing the project. So the value model models the establishment and spread of exotic pests and diseases and their impact on market and non-market assets across Australia, given different states of the Commonwealth biosecurity system. So it first models the establishment of pests, so pests coming in, so leaking through the biosecurity system and then establishing. Ideally, you would expect that the probability of establishment with the system on is less than when the system is off. This then, once it establishes in the model, then the model simulates the spread of the disease or pest across its host range. And then we calculate the impact. So if this disease or pest gets to its host, we expect it would reduce its yield and therefore cause a yield loss, or which we convert to a dollar value. So this is the original pests and disease categories of the value model. There are 40 functional groups with 39 exemplar species. These groups are broadly combinations of pest and disease taxa and host sector, except for a few high impact pests and diseases such as foot and mouth disease and giant African snail. So this categorization was kind of for modeling purposes for that whole system modeling. The value model had 16 asset classes as well that we looked at. These fall under the 5 broad groups of agriculture, environmental regulating services, environmental, cultural, and social amenities, domestic animals, and infrastructure. So the value model overall has a lot of inputs, and the inputs are the focus of this project. So it requires those pest and disease establishment probabilities that I mentioned earlier, as well as pest and disease spread rates, pest and disease impacts the assets, the hosts, asset values, as well as the locations of these assets across Australia. So this information, a lot of it is sourced from the department's CEBRA model, which in turn was informed a lot by a lot of ABARES work. And there was also extra information sourced from scientific and grey literature and other databases. So this then is all put together to the value model, and it produces out some monetary values about this, the system. So regarding asset values in particular, we do note that we're taking an economic approach to environmental and societal impacts, and we're putting a dollar value on these. The dollar values of these environmental and cultural assets are like such as the value of water or erosion control or recreation or indigenous values that basically estimated from scientific literature sources and using benefit transfer. We do understand that economic approach is limiting. However, it does allow us to define a common language for all these assets, and it allows us to include environmental impacts with agricultural impacts. Like a value, some value would be better than no value in this kind of situation. And so it altogether it gives us a better understanding of the high level understanding of the system and the assets that the system is protecting. So this and other assumptions does mean that these consequence estimates are useful for system modeling purposes, but might not be, and some other purposes, but would not be suitable for every purpose. So in Project 23C, is about developing a comprehensive approach for consequence estimation for system modeling purposes. We had kind of 3 parts to this work. The first part was to extend the suite of exemplar pests and diseases based on and aligned with existing departmental priority pest lists and pests that are of key interest to project stakeholders. So, for example, we looked at the national priority list of exotic environmental pests, weeds, and diseases. We obtained pest parameters relating to the agricultural or market consequences for the new pests and diseases that we added. And we also developed a plan to update parameters for environmental consequences with a case study. So the first thing we changed was the pests and disease list. We were really looking more at the species rather than the functional group. So we changed angler leaf spot to strawberry angler leaf spot. By making it more precise, it's getting information for it is more like more clear. We removed Russian wheat aphid because it's no longer controlled at the Commonwealth filter. Termites was converted to Formosan subterranean termite, which is one of the termites on one of the priority lists. Thrips were removed because they were too broad to form precise economic estimates, and we also had pests that already affected the same or similar crops. We converted just generic Cyphorus to Cyphorus brachylaema. We removed generic Hymenoptera and replaced it with Asian honeybee, and we also removed generic Diptera, noting that we already had flies such as papaya fruit flies and other similar pests that act on similar hosts. And then we added new pests and diseases. So based on the various national priority pest lists and feedback we got from DAFF and DQ, subject matter experts, we added some new individual pests and diseases, including especially those of environmental concern. So brown marmorated stink bug, myrtle rust, Didymo, carnal bunt, great phylloxera, Salella and its vectors, Asian honeybee, Wolong bing, spiderwing Drosophila, polyphagus short-hole borer, lumpy skin disease, and boa constrictor. And so as part of this project, we were looking at adding new finding the parameters for these new pests. So this is what the state was before. As part of the value model to update it, we did a lot of information. We got a lot of information from scientific and grey literature, especially CABI and the ABED publication library. And we also conducted an expert elucidation workshop in Canberra earlier this year to get some parameters that we couldn't find elsewhere. So this is the table of the new parameters, which is in the report. These are, like I said, agricultural parameters. Like we need parameters. These parameters are needed to simulate the actual spread of the pest itself, as well as the agricultural impacts. Project 24C is now the continuation of Project 23C, and that one is making updates to the agricultural parameters for the original pests. So that's like the first two stages of this project. The second stage was to develop a plan for updating environmental consequence estimation. We want to explore different methodologies and implement some of them in a case study to kind of see which one was most suitable for our purposes. And we're looking at regulating services in particular rather than cultural services. So typically there are three main methods for estimating environmental consequences because, So the first one is expert elicitation, and this is actually the original method for the value model, which was sourcing data from triple array model and ABES. So that requires 10 to 20 experts and time. So we had a workshop earlier this year in February, and we had 4 pests and 1 parameter per pest, and that took an entire day. So as you can imagine, if you have over 40 to 50 pests and you want to update this, every several years, there's going to be a lot of workshops and a lot of time. Another method is choice modeling, which requires hundreds of participants. It's well regarded, but it's timely and even more expensive. And benefit transfer is also a good method, but it does require previously conducted choice modeling experiments to have existed, and for those experiments or papers to be transferable to Australia. So these methods all require a lot of time and experts or people, and so we wanted really to make a method that was more comprehensive. They can be more comprehensively applied across various pests, disease, and assets, and ideally more scalable and also like more sourceable. That uses data. So we ended up choosing myrtle rust and its impact on carbon sequestration as a case study. So myrtle rust is basically chosen through consultation with DAFF and DQ. So a little bit about myrtle rust. It's caused by the fungus Astropocenia cdi. It causes different leaves, branch defoliation, diebacks, stunted growth, and even plant death in certain species. It affects plants belong to the Myrtaceae family. So some examples include eucalyptus, willow, myrtle, bottle brushes, and paperbarks. It is spread by wind and human movement, and there are over 9 strains of myrtle rust. So the pandemic strain is already in Australia since 2010. We're kind of assuming that there's an exotic strain or a strain that is as bad, if not worse, than the current strain that we have. So we end up looking at 3 different candidate methods. One was mapping from the National Priority Pest List of Exotic Environmental Pests, Weeds, and Diseases dataset. So they had a dataset based on expert elicitation that then informed their the priority pests. We also used benefit transfer based on a paper that was the report that we found, and as well as contribution modeling, which is a new method that we developed to model species level contribution to carbon capture. So the EEPL has pests and ranks pests and the impact based on a scale including like major, moderate, minor, and so forth. So what we did was that we gathered regional pests from the value model that also appeared in the EEPL, and we got the parameters of environmental impact. And we basically fitted a curve of that based on what the EEPL had stated it to be and what the value model had it to be. And then myrtle rust's impact, according to the EEPL, was massive. And so if we map that over to the value model, then you would expect a parameter value of approximately 20%. So that's the first method. The second method was benefit transfer, based on a New Zealand choice modeling experiment with over 500 respondents. So they looked at respondents' willingness to pay for management to avert several different possible outcomes caused by myrtle rust. We looked at impact to native forests in particular, because we're looking at carbon sequestration that would be directly impacting forests rather than, say, heritage or iconic trees. And we adjusted for things such as population size, currency rates, income levels, and we estimated environmental. Based on this, we estimated it to be between 0.6 to 2% of damage, so a lot smaller than the previous method. And finally, contribution modeling. So there are 3 different components to contribution modeling. There's the we need to know, it basically works from kind of first principles. So where are the trees, which trees does myrtle rust affect, and when it affects it, how does that reduce the amount of carbon that is stored per year? So we need to know what the plants are and their annual contribution to carbon sequestration. We need to know how myrtle rust affects the trees and therefore the carbon that is stored per year, and then to kind of value it in the value, to fit it into the value model framework, we need to know the valuation of carbon sequestration. So we looked at the NVG level, and we basically found different plots of plot data in different NVGs and scaled it across those major vegetation groups. So this included the biomass plot library, the carbon mallee stem diameter, height, and above ground and woody biomass data, Robson Creek rainforest data as well. We combine that with growth rate data. So basically we have data about what the trees are now and then what they will be in a year. You put them to allometric equations, which basically convert things like diameter and height into biomass. And so with the growth rate data, we have the vegetation data with the current biomass. With the growth rate data, we have the predicted future biomass, and therefore what the annual carbon sequestration is per genus. So how much extra carbon is getting kind of stored in these trees. So this is the results. We get the per hectare estimate of carbon sequestered by genus within each major vegetation group. We see that we don't have all of the major vegetation groups here because some of them didn't have any data. We will assume that the myrtle rust, the carbon loss in those is 0. So we see that green, if it's eucalyptus, is the major contributor to carbon stored per year. And this is because they're very abundant in these areas and also very big compared to other trees. They also happen to be susceptible to myrtle rust. So as you can imagine, there will be a pretty major impact if myrtle rust were to infect all these trees. So the next step is now to understand what the myrtle rust's impact is. We looked at a lot of papers, sources from the literature about tree death, percentage branch death, and reduced tree growth. All of these would stop or hinder the amount of growth you would get. Combining that with the annual carbon stored per genus in the previous section, we can then estimate the carbon loss due to myrtle rust, basically just multiplying the values together. So these are the top 3 genera that had the largest carbon loss due to myrtle rust, and the percentages represent the average impact percentage gathered from the values in the literature. So we did have some information by species, but then we had to average everything by genus due to lack of data in general. So the top 3 are eucalyptus, syzygium, and rhodamia. Myrtle rust, eucalyptus basically is a dominant factor in everything because so even if the impact to eucalyptus is less than rhodamia, there's a lot more eucalyptus, and therefore this impact is a lot more important. Then next there will be the valuation stage. So we had the carbon loss due to myrtle rust and the annual carbon sequestered, as well as the valuation of carbon from the value model. And together we can basically calculate the value loss due to myrtle rust's impact on carbon sequestered. So like I said, if we didn't have any data, we would basically have this as 0, and the total value loss would be 0 as well as an underestimate. So here are the reductions of carbon stored in some of the different NVGs. The values of these are actually very similar. This is because they're predominantly eucalyptus. And then across all NVGs, when we summed it up, we found an overall reduction of 10%. This is assuming that if myrtle rust spread everywhere in Australia. And using published values of carbon sequestered, this would result in a loss of $2.9 billion. Again, assuming that this it just spreads everywhere right away. So there are some assumptions, advantages, and limitations to this method. We had a lot of assumptions and simplifications, such as homogeneous vegetation groups, and we also simplified trees in the same genus because we didn't have enough data to go at the species level, but we could have, hypothetically, in this method. The advantages of this method is that it applies quite specific estimates at the genus and MVG specific level, and it could potentially be rolled out to other environmental assets or pests. So we already have information about carbon sequestered for trees across Australia. If instead of myrtle rust, we had another pest like polyphagus, short-hole borer, and we knew its impacts on different species or different genuses, then we can input that in instead and calculate its impact to carbon sequestered in Australia. And it does require there are a lot of limitations though. As kind of mentioned previously, there's a lot of data. It needs a lot of data, and we have a lot of missing data. And contribution of plants to certain services can be very complex. So with carbon, it's very clear, but if you want to do something like erosion control, it's less clear because erosion is also dependent on things like the weather, the soil, the landform, and stuff like that. So, however, it still does do a very direct estimate and uses data from field studies. It's reproducible. It's not like expert elicitation, which is less clear how values are obtained. This method, like I said, is applicable to carbon sequestration impacts due to other pests and diseases if we can get the data. And we do believe this method can be extended to some other ecosystem services, provided data exists and provide we have kind of the mathematical understanding of how plants or other things affect those services. And it fills a gap in climate science and natural capital research. It relates the issues to things like climate. To compare the different methods, in order to inform our implementation plan, we saw that these different methods had different levels of ease and also different values. Contribution modeling kind of predicted a value in between the other two. Good thing about the EPL mapping is that there are many pests on it. There's been a lot of work already done to get that data set as scores for both environmental impact and social amenities, and it's easy to convert those scores, either with the method that we use or a different method. But however, there are no numerical estimates, and something like a major impact can actually have a pretty wide range in terms of percentage impact. It can go from 50% to 100%, but it's not clear. Not all pests are on the EPL, and it can have it is potentially inaccurate and vulnerable to extrapolation. With benefit transfer, the good thing about benefit transfer is that there are established techniques and based on choice experiments that gather results from hundreds of people. But then it assumes that those experiments exist. It assumes that those studies are applicable to Australia. New Zealand is fairly similar to Australia culturally, but that might not be the case for other locations. And the measure of interest may not be the same. So, for example, with the New Zealand study, they looked at protection to native forests, but not to protecting carbon sequestration in particular. So it's slightly different. With contribution modeling, as I mentioned before, it helps make updates to other pests more efficient in the long run, and it could be rolled out to other environmental services, but it does require a lot of upfront work and data, and it might not work for other services or might be quite more complex for other services. So the point of a lot of this case study was to do the implementation plan. So in the report, we have the implementation plan for to update pest specific parameters as well as environmental assets. This is just a snapshot of what we had. So we had something like, okay, how would you update pest impact environment assets? You would prefer to do contribution modeling, reproducible workflow, and we estimate that will take 130 hours per new asset and 30 to 50 hours per new pest to basically find the information and put it in. But once you do it, you can basically roll it out more quickly. Another thing we noticed is that we should probably extend the environmental asset list and reevaluate it and target key priority gaps, such as, for example, biodiversity. It's not very clear how that is included inside the assets that we have. So the approach to do this would be to assess the list and then do some stakeholder consultation with departments, states, and territories, and other organizations. We expect about 13 hours to kind of run those consultations. Another thing we've noted is that in the regional value model, also noticed this is that the indigenous asset valuation is questionable. As mentioned, like we are taking a economic approach. It is not the best approach for all situations, but for this, it's better to have value than no value. And so we would, our suggestion is to kind of review other projects that have looked at evaluating indigenous cultural connections and following advice given by Menner et al. In their paper. But that would be a much more long-term project in order to kind of sensitively value it in the framework of the value model. As part of this project, we did rerun the value model just to make sure that things were working. So we kind of see that in red, we have the system damages over time. And if you had the system on, then the damages is less. That gap is basically the value of the system. So the new pests and parameters have made some impact to the consequences, but we are still, the other key parameters are still being updated right now. This and a lot of other things are all can all be found in the project. So it's on the CEBRA website. And to kind of conclude, so in this project, we added 12 new pests, removed 4. We had new parameters, agricultural parameters for the new pests, and we looked at estimating carbon sequestration impact due to myrtle rust. We developed an implementation plan for environmental parameters. And in the next steps, Project 24C is estimating disease parameters for the old pests. And so ideally, they will update all the agricultural parameters for all the old pests. And then of course, there'll be more steps to update the other parameters. And finally, I just want to acknowledge the financial support provided by DAFF and MPI, as well as the advice of many people who attended a lot of our stakeholder workshops, as well as the expert elicitation workshop. And that's it. Thank you.
Amazing. Thank you, TK. And thank you, Pip, as well, for joining us today. We'll open up for questions. If anyone's got any questions, feel free to pop them in the chat, as well as you can raise your hand as well. So,
while people are thinking of questions, I might jump
absolutely.
in with a comment just to thank TK and also Meryl, Chris and Tom. It was a great project to work on with you, and appreciate the team's consultative approach to this work. And one thing that we really valued as a deliverable was that very detailed implementation plan with the estimates of time and effort required to undertake each of CEBRA's recommendations. That's super useful to us. So thanks again, team.
And I have a question in terms of, how often would you ideally need to update the model to stay current? I mean, in a perfect world, we'd want to be, constantly updating it, but, considering the commitment that's needed to update, is there sort of like a long-term plan that it's, like once a year or as needed? Do we sort of have a bit of an estimate on that?
It kind of depends how fast the situation changes. I think I guess if it's not per year, then every 2 to 3 years or every 5 years. Some things may change slower than others, and so it will have to be like on a case-by-case basis, I think.
Yeah.
And maybe I can add there, I think our perspective on that is that the overall consequence estimates would probably be due for an overall update every 5 years or so, but informed by, for example, intelligence findings. So if there was an intelligent finding indicating a novel pest that was a new threat, and we assessed that that would greatly affect the functional group of pests that that belonged to, and then that one could be updated, you know, out of session, I suppose.
Excellent. I do have another question. I guess by running the value model again after doing these updates, was there anything surprising, I guess, that came out of running that analysis?
I would say not very surprising. It had a minor change, but it's also like it's as expected, I guess. Like there wasn't a major change when we reran the value model.
Excellent. Now I'll just check the chat to see if anyone's got any questions. There's nothing in the chat. Anyone want to? Oh, there you go. Snuck in there. So Kevin's got. So Xylella has not been modelled yet.
It's in the value model. It has spread and it has impact to agricultural assets, but not to. It might not have any impacts to environmental assets at this point. I don't know if that's what your question is.
Yeah, I guess I wasn't thinking about environmental assets. I was thinking more about modelling the impact more in agricultural terms. But we do have a list of over 20 native species that would be impacted.
Yeah, so the value model already includes its impacts to agricultural assets. So if I go back, okay, here. So Xylella affects blueberries, almonds, pecans, wine, oranges, lemons and limes, mandarins, grapefruit, and olives in the value model. So these are basically different industries that the value model incorporates into its like host class. Does that answer your question?
I assume the modelling is to try and predict a real-time occurrence.
Yeah.
The problem with Xylella is that every time it pops up, it's surprising.
Yeah.
So
the probability of it coming in is random. So the probability here is like 0.5% or 20% system off, and it just in a model it just randomly appears near population centers in where its host exists, right? And we run these simulations many hundreds of times, and it may pop up at different times and different locations in the simulations, and then we just typically average all the results together.
Okay, I might have a different argument for its presence and absence that you might not have considered.
Yeah,
just wondering if we should talk later.
Pip said we're not really forecasting anything, and it's more about like the high level overview rather than the precise Xylella impact. So if we wanted to like model Xylella in particular, we would have actually its own model to have all its unique features and how it uniquely moves. But overall, the value model is much more broad than that, and in order to like capture a lot of pests, we have to basically simplify a lot of how they spread and how they get in and how they impact hosts and stuff.
Does this work tie into department responses? Like you would consider the model and then the department would consider how far they would go to either have surveillance, prepared to pay for perhaps responses. Is that where it's heading?
Pip can answer this better than me probably, but I think the answer is no to that. It's not a particular model for it's not like a response model. That
Right.
would be a different kind of model. This is too broad for it to be a response model, basically.
Okay.
Yeah, agree. Yeah, so you would need a different tool to tackle that very important question. Yeah, it's not this. These models do not work at that level of granularity. They're not designed to answer that question. Yeah.
Okay. All right. Thank you.
Thank you.
Okay. Don't see any other questions coming through the chat. So we can wrap up, I guess. So once again, thank you TK and Pip for joining us today, and thank you for everyone who jumped online today. We very much appreciate your patronage of joining us for our monthly CEBRAnars. And as we've said, the recording will be available soon, and we'll send that out to all that registered. And we've got our last CEBRAnar of the year next month at the end of November, 28th of November. So to get details on that, you can follow us on Humanitics. So once again, thank you all, and have a lovely Thursday. Bye.
Thanks,
Thank you,
everyone.
everyone.
Bye.